All right, guys. So this afternoon with probability from grade 10 to 11 isn't that much different. We're just tightening the knob on the difficulty level. Like leaving a few stuff out from your Venn diagrams that you need to go and find by yourself, which we're going to consider as like an unknown variable, like an X or Y, or whatever you want to make it. It's going to be needed for you to really know your probability rules, definitely know what the different concepts are, when certain events are mutually exclusive or when they're inclusive, when they're complementary, when they're exhaustive, all that type of stuff. The not rule, the addition rule, the independent rule. That rule gets asked a lot this year, especially with your two-way tables. So let's not waste any more time. You guys have gone through this. So basic idea, what is probability? Probability is the probability of an event. That's what P of E stands for, is the number of possible times an event can occur. That means the number of outcomes in that specific event. And remember, with number of outcomes, we use the letter N. If we're saying NE, for instance, we're talking about the number of outcomes in this event E. For instance, if I'm talking about rolling a dice and landing on an even number, how many even numbers are there on a dice? There are 3. It's 2, 4, and 6. So therefore, the number of outcomes in the event of wanting even numbers is 3. But if we're talking about NS, we're talking about the number of outcomes in the whole sample space. In that case, we're talking about every single possible outcome when it comes to that dice. I mean, that means all the levels on the dice. That means 1, 2, 6. That's why you have 3, because you have 3 even numbers over 6, because there are 6 possible outcomes in the whole thing. And when it comes to your Venn diagrams, please remember you get different types of Venn diagrams. You get outcome-based Venn diagrams and you get probability-based Venn diagrams. With your probability, the probability of a sample space is always equal to 1, and all the numbers on the inside have to count up to this 1. So they'll all be very fractional. And when it comes to your number of outcomes in your sample space, that can be any number. I mean, it depends on the event. It depends on the situation. When I'm talking about rolling a dice, we've got 6 different inside of the Venn diagram, and all the numbers which are inside of the Venn diagram have to count up to 6 in the end. So just be aware of that again. All right, let's move on. Again, S, we use the letter S for sample set or sample space. A, that could be event A. Event A can be anything that we want it to be, anything that we desire, but A can be used as a variable to summarize the whole concept of an event. Same with event B. If we're talking about this symbol over here, it's talking about union or the word or, right? And or means plus. That's very important. So if I'm talking about the probability of A or B, then I'm talking about everything and in A or B, almost encapsulated in this bubble of A and B together inside of this bubble, and everything that is inside of A, B, or even A and B, that intersection between the two. Speaking of intersection, we talk about intersection with this symbol, means intersection, but we can also use the word and. So if you see in your paper saying A or B, they're talking about the union. They're talking about all of that together. They're talking about A and B, talking about intersection, where those two have something in common. Say, for instance, with your dice again, you have even numbers and numbers greater than 3. Then 4 and 6 is something which those two events have something in common, because 4 and 6 are both even numbers, and they're both numbers which are greater than 3, for instance. So just be aware of that. Then again, with relative frequency, which is not really very much asked in senior mathematics, we actually work with theoretical probability, not experimental probability. But experimental probability is really just the physical action of doing what you want to go and experiment with. I'm talking about what is the probability of rolling a dice on an even number. You will be physically rolling that dice and marking down what the answers are. But the idea with experimental probability is that the more you do the experiment, the closer you will get to the theoretical probability of that specific event. Right. The addition rule. This is very important. This is applicable to your number of outcomes as well as the probability of a certain outcome. And that is that the number or the probability of A or B is equal to the number of A or the probability of A plus the number or probability of B minus the number or probability of A and B. Now, why is this? If you look at, for instance, a Venn diagram, let's think about it this way. Now, A or B refers to this. That is A or B. Everything inside of that altogether, that's A or B. Now, if you think about the addition formula, what is it saying? It's talking about A, let's say this is A. It's talking about A, and it's talking about adding B. But if you look closely, there is a part which is being added twice, which does not add up to the whole encapsulating of that red bubble that I've drawn over the two, which means we're actually over what we're supposed to be. So we compensate for that double addition by subtracting the and once. So that is always very helpful when you're not with a Venn diagram, but you're just sitting with the probabilities as numbers in front of you or the number of outcomes in front of you. Right. When are events mutually exclusive? They are mutually exclusive when there is no intersection between the two. What does that mean? That means the probability of A and B in a mutually exclusive situation is 0. There's no possibility for any outcome which is a commonality between the two. Therefore, the probability of that is equal to 0. Same for the number of outcomes between the two. But for the OR, this is what's nice. The OR, again, should be this. Because there's no intersection between the two, there's no chance of doubling something which is common between the two. You can just add A and B together. So that's why the number of outcomes for A or B will be the number of outcomes in A plus the number of outcomes in B. That will give you both of those. Same for the probability. The probability of A or B in a mutually exclusive situation will be the probability of A plus the probability of B. Nothing much around that idea further. Then an exhaustive event. An exhaustive event, which are events, events are exhaustive when they cover all the elements in the sample set. I mean, think about it. When you're exhausted, when you've used all your energy, everything that you have to give, that means you are exhausted. Now, it's the same thing here. When the sample space is given everything it has to the events, then the events are what we call exhaustive. Now, complementary events. Events A and B are complementary events if they are mutually exclusive and exhaustive. This is actually perfect with what we see over here. These two, A and B, they are exhaustive. Why? Because not only are they are complementary, because they take up all the data, which means they're exhaustive, but also they are mutually exclusive, which means they're complementary. And in this case, the probability of not A will be equal to 1 minus the probability of A. I mean, what is not A in this case anyway? It's B. So if we take 1, which is the probability of the sample space, and we subtract A, what are we left with? We're left with B, which is not A. And it's the same vice versa for B anyway. Right. Now, independent events. What are independent events? Independent events are events which do not influence one another. Example, for instance, you're throwing a dice and you're throwing a coin or flipping a coin. Those two are two different items being exercised with in two different ways, separately from one another, so they will not influence one another. Therefore, the two outcomes or probabilities received from those two items are therefore independent. But if you think about it this way, you've got a bag of balls. So now you've got 10 balls inside of this. You've got 4 blue balls and you've got 6 red balls. Now you take out a red ball and you don't place it back. The probability for your first red ball is very simple. Or for your first draw is very simple. But your probability for your second draw will be influenced by that first draw, seeing as you haven't put it back. For instance, your sample space has changed, 1 less. And because you drew a red ball in the first one, the number of red balls you have now is 1 less. So that means the fraction that you're going to set up, or the ratio that you're going to set up for your probability, will also need to be considered, because these two events are dependent on another. But independent has a very, very nice rule how we can test independence, and that's this rule, which we call the product rule. The product rule states that the probability of A and B in an independent event situation will be equal to the probability of A times the probability of B. Good. Now, dependent events, just spoke about what dependent events are. Tree diagrams, you guys know how tree diagrams work. I'm not going to go through this example because you guys have done an in-depth with this. There's another example. I want to do exam stuff this afternoon. I know you guys want to do it as well. You guys have done tree diagrams. You've done the in-depth. I've done the in-depth with Afrikaans. So I'm going to run through this. Just want to mention, with tree diagrams, it's very important to read through the paragraph. Sometimes we can interpret how the tree diagram can look in many different ways because of the way that we read it. Please read it carefully so that you understand how the tree diagram should look. Two-way contingency tables. You guys have done this since grade 9. This is really not a problem. You guys are actually very aces in this. We found that grade 11s are very, very good with this. Just make sure that your rows are totaled and your columns are totaled. That will be very important for getting the probability. But I don't want to say too much about this because you've gone through this in depth here. Here's another example, in depth. You've already done that in the in depth, already done this in the in depth. Right, with your Venn diagrams, this slide over here, which is in your notes, is so useful for getting to grips with what are they talking about if they are saying, for instance, V and M, V or M, not V and not M. For me, the easiest way to think about it is the whole concept of intersection, in other words, where they cross, or union, in other words, everything surrounding them. So when you look at these different ones over here, make sure that you understand what they mean. And the best way of understanding it is actually by just closing up this slide, or this one frame in the slide, and just close this up and go and draw two events which are crossing like that, and name it A, B, and now go and apply this, what they want, what they say, like A or B. What does that mean? That refers to everything inside of this, as if they are joined together as one thing. That means all of this together. Same with the others. You can see here, for instance, the not rule. The not means everything outside of it. And they're talking about not V or M. Then obviously this is V or M. So that means everything outside of it. Another way to express this is by saying not V and not M. What does that mean? Here's V. Here's everything outside of it. Here's M. Here's everything outside of it. Now the question is, where do the outsides cross each other? Yes, they cross each other here on the outsides of both of these. Right, V and M, very easy. You guys know that that's the intersection between the two. They're talking just about M, that's easy. They're talking just about V, that's easy. Not V and M. So here's V, but this is the outside of it, meaning not V. Here's M, but where is V and M, V and not M intersecting with each other? Yeah, that's where V and not M are intersecting with each other. Then not M, just explain that. V or not M. So very important. Here's V, everything inside of that. Here's M, but we're looking for not M, so everything outside of that. So we're looking for everything outside as well as V. So that means that's this, also everything outside of M. Then not V and M. I mean, if this is V and M, then we want everything outside of it, right? Then not V or not M, that means here is not V, and here is not M, and we want everything which is not V, not M, and that means that intersection then falls away. Right, another Venn diagram example we're going to do in the exam once you guys have run through this. Here, just want to mention with this example too, there is a situation where you have this unknown part, and therefore you're going to have to set it equal to X and get things in terms of X and use the sample space, for instance, the sum of all those outcomes or the sum of all the probabilities to set it equal to either 1 or set it equal to the total number of outcomes in your sample space to set up an equation so that you can go and work out X. But we'll get to that in the exam questions as well. Another still example. Great. Done with the recap. Let's get into what we're here for this afternoon. We're here. We haven't covered it at school as yet, so it may be a bit harder for me to answer questions. That's fine, Killen. I'm going to help you out with this stuff. Today is a finals session, so today is more a recap on the notes because you guys have done the in-depth. So please, if I'm going to ask you a question, I'm going to walk through it with you. But if I'm talking to the other learners and there's anything that's troubling you, stop me. If you have a question, let's do it. I'll try and help you out. Okay, is that cool, Killen? Right. Okay, guys. So I just want to switch off my annotations. You guys have all these notes over here. You have finals, maths, paper 1, grade 11 questions. After your number patterns, you'll find the probability section. This is on page 4. I really love it if you guys have this in front of you because I'll be scrolling like this and this. It'll be really bad if I'm trying something over here and I want to refer back to the question, asking you something, and you want me to go and scroll back. That's just going to waste a little bit of time. So please make sure you have your notes in front of you. Cool. So let's get to work. Question 2.1, DBE, November 2014, question 12. They say Babalo has a bag containing 80 marbles that are either green, yellow, or red in color. 3/5 of the marbles are green and 10% of the marbles are yellow. Babalo picks 2 marbles out of the bag, one at a time, and without replacing the first one. Now, they ask, how many red marbles are in the bag? Okay, so Humara, are you going to help me out? Humara, are you there? Okay, Deanna, you gonna help me out?
Yes, sir, I'm here.
Okay, cool. So they say Babala has a bag of 80 marbles, and they tell me 3/5 of the marbles are green and 10% of the marbles are yellow. So how does that help me out to find out how many red marbles he has?
Okay. 3/5, if I put that as a percentage, that's going to give me 60%.
All right, so 60% of the 80 marbles is, they say, green. Okay.
48.
Say again.
48 marbles are green.
So therefore 48 marbles are green. So I just want to number this quickly. This is A. All right. And what will you do further?
My yellow are 10%, so 10% of 80 going to give me 8. If I take the 48 minus, and I minus that from the 80 and the 8, sorry, 48 and the 8.
All right. And what does that make up?
That gives me 24 red.
24 marbles are red. Okay, cool. That's 2 marks. You can help me with this next one as well.
Yes, sir.
Right. So I just want to switch off this aircon. It's getting pretty chilly in here. Right. So they want me to go and draw this tree diagram. Now remember, he's picking 2 marbles out of the bag, one at a time without replacing one. Okay. Now let's start. Now remember, you can't pull out marbles without you being there. So this is you. You ready to pick some marbles?
Yes, sir. The 48 was gotten, you minus the, okay.
I'm just checking here. Tando is asking, where did we get the 48? All right, Tando, if you want to know where the 48 came from, they say 3/5 of the marbles are green. So that's why what we're going to do is we're going to take the 80 marbles. We're going to work out what's green. So 3/5, that's 60%. And 60% of 80 is 48. Then they also said 10% of the marbles are yellow, which means it's 8. And then we take the 80, we take out all the green marbles, we take out all the yellow marbles, and we're left with 24. Is that fine, Tando? All right. Okay, back to this, Deanna. So here you are. You're gonna pick a marble now, right? What are the possible outcomes of color marbles that you can get from this bag?
Well, you can get green, yellow, or red.
So you can get green, yellow, or you can get red. Now, what is the probability of getting green?
48 out of 80.
Yes.
60%.
Right, so that's 3/5 actually. Now,
Yes.
well, it's gonna come down to 3/5 in any way. So that means if you couldn't get this one right, you'd still be able to go and figure that one out. All right, yellow marbles. How many yellow marbles? What is the probability of finding a yellow marble?
8 over 80.
That's 8 over 80, which is just 10%. And then for the red marbles, what's the probability of getting a red marble?
24 over 80.
24 over 80. All right. Now, let's say you pick the green marble. Now you're ready to go and pick another one. So what are the possible colors that you could pick after you've picked that green marble?
A green, a yellow, and a red.
Green, yellow, and red. But now we need to consider we didn't put that green one back. So what's the probability for picking a green one in the next round?
47 over 79.
Very good, over 79. Yellow?
It's still 8 over 79.
Over 79. And red?
24 over 79.
24 over 79. Good. Now let's say you picked a yellow one. What's the possible outcomes? Still green, yellow, and red, right?
Sir?
Right. So what's the probability for choosing a green one on the second round?
Green, 48 over 79.
48 over 79. Yellow,
7 over 79.
7 over 79. And red,
24 over 79.
24 over 79. Very good. Right, now for the red one, still second round, you still can pick green, yellow, or you can pick red. But what's the probability of choosing green on the second round?
48 over 79.
48 over 79. For yellow?
8 over 7. Yeah, 8 over 79.
Yeah, 8 over 79. But for your red?
23 over 79.
23 over 79. Very good. Great. Tree diagram done. Now at C, they ask, what is the probability that Pablo will choose a green and a yellow marble? Now remember, green and yellow doesn't necessarily mean in that order. It can either mean first green, then yellow, but it could also mean what?
Yellow and green.
Yellow and green. So we need to think of the probability of green and yellow, or yellow and green. And or, I said earlier, means what?
Or is plus and is
Or is
multiple.
plus. Yes, very good. So we're going to take green and yellow, work that probability out, and then yellow and green, and work that probability out, and then we're just going to go and
Add them together, get it out of 100%.
Yeah. All right. So when we move down the branch, can you remember what are we going to do with these probabilities?
You want to get your green and your yellow, and then you want to go to your yellow branch and get yellow and a green. You want to multiply together.
So your yellow and then your green. But as we move down the branch, how do we put these probabilities together as we move down the branch? Can you remember?
Multiply.
We
Unless I'm
multiply.
understanding.
Perfect. Yeah, we multiply. So the first one, we're going to say 48 over 80 times
8 over 79.
8 over 79 plus, and the next one,
8 over 80.
8 over 80 times
48 over 79.
48 over 79. Right. You got a calculator there?
Yes.
I've got one as well. I'm working it out on this side. So let me know what you got. Let me see if I get the same. I'm ready. What have you got? Give me the fraction first before you give me the decimal.
Okay, so just hold on. 48 over 395. That's
Very
all added
good.
together.
Yeah. And what is the decimal answer in the end? Round it off to 2.
0.12.
0.12. Diana, thank you very much. You're a champ. Appreciate it. All right. Let's look at this next one. Victoria, you're going to help me with this one. Victoria, are you there?
Hello, sir.
Hi, how you doing?
Good, and you?
I'm good, thanks. It's Friday.
Just excuse my voice. I am a bit sick, but
no worries.
you know.
say what you can say, and if you can't say it, just type it. It's fine.
Okay, perfect. Thank you, sir.
Right. Let's look at this one. So they say a survey was done among 80 learners. All right. 80 already tells me what?
That there's 80 in total that are taking
So
part in the experiment.
the number in the sample space is therefore 80. Do you agree?
Yes, sir.
All right. Then they say a survey was done among 80 learners on their favorite sport. The results are shown below. Now they say 52 learners like rugby, 42 learners like volleyball, etc., etc., etc. Now, I'm already getting the feeling, and this feeling is being confirmed here, that we should draw a Venn diagram.
Yes.
Right, so let's start with that. Now, Victoria, before you start telling me what to do, I just want to tell the rest of the grade 11s. Grade 11s, if you are working with 3 events here, like here, for instance, they're talking about rugby, volleyball, and chess. It's better to go and draw them initially as if there will be a part where a learner can take part in all 3, right? Don't hesitate on that. If it comes out that there's no such learner, then just leave it open. Then that just means there's nothing there. So go and draw the circles like this. And we're going to call this one rugby, volleyball, and chess. All right. Diana, Victoria, let's look at this one. They say there are 52 learners who like rugby. So where's that 52 going to go in my Venn diagram?
So first you would take 80 and then minus it by the number of players that play rugby. So then you would say 80 minus 52.
So they say 52 learners like rugby. I mean, can't we just go and put that somewhere on the Venn diagram just like that?
No.
Why not?
I'm not 100% sure, sir.
Well, let me put it this way. I like the fact I can feel your hesitation, but and I like the fact that you're hesitant, because the thing is, if they say 52 learners like rugby, does that mean 52 learners are going to come here? Let's say the first place, second place, third place, or fourth place?
No, sir. They would only stick to the rugby.
Now, does that mean just in this first place?
Yes.
Can I maybe ask you this? I mean, how do you know the 52 learners in here only like rugby?
Yeah.
You see what I'm saying?
Yes, sir.
The fact that we don't know in what way they like rugby, the only thing that we can do is say that, okay, whatever is going to be here, 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 all of those should add up definitely to 52. Does that make sense? Hello, Victoria, are you there?
Yes, sorry, I was having a few problems, as you can hear in the background.
That's fine.
Can I just type, sir? Because it's a bit noisy this side.
Okay, that's fine. I'm going to carry on. I'm going to ask Mamelo to help me.
Okay,
Mamelo? That's fine, no worries. Mamelo, you there?
Yes, sir.
Hi,
We're not done covering this topic though, so yeah.
That's fine, no worries. We're gonna let's treat it now as like an in-depth, right? So obviously the fact that we don't know how many of the 52 learners like rugby and volleyball, for instance, or like rugby and chess, for instance. The only thing we can say is that this whole circle here of rugby, this whole circle here, regardless of what this, or this is, all of these should add up to 52. Okay.
Yes, sir.
All right. So let's look at this next thing. The next thing they say is 42 learners like volleyball. So what does that mean to you? Where should we put this 42? I mean, here's the circle of volleyball there. Should the 42 be placed in this first, second, third, or fourth place?
Well, sir, it should total up to 42.
It should total, yeah. So again, we don't know in what specific way these 42 learners like volleyball, but we know all of this should add up to 42. You agree?
Yes, sir.
All right. Now they say 5 learners like chess only. So this 5, I mean, if we look here at the circle of chess, which is this circle over here, should the 5 be in the first, second, third, or fourth place?
I think it's in the first because they said only.
Yes, perfect. So this is going to be 5 in here. Perfect. Right, so that's done. Now they say 14 learners like rugby and volleyball, but not chess. So here is rugby and volleyball. Let me just get another color pen. Here's rugby and volleyball. This part over here. But they don't like chess. So does that mean this 14 comes in this first or second spot?
First spot.
The first spot. So this is going to be 14. Brilliant. Yeah, you're doing very well so far. Now it says 12 learners like rugby and chess, but not volleyball. So rugby and chess. Here's rugby and chess again. There's rugby and chess, but they don't like volleyball. So does this 12 come in the first place or the second place?
In the first place.
In the first place. Good. So this is going to be 12. Now they say 15 learners like volleyball and chess, but not rugby. So here's volleyball and chess. So does the 15 come in the first or the second spot?
Second spot.
Second spot. So here we go. This is 15. And now they say X learners like all 3 types of sports. So where do you think X is going to go on our Venn diagram?
The center spot.
The center spot. This is going to be X. Right. And then they say 3 learners did not like any sport. Now, where does that go?
In the box, I think.
In the box, now outside of the bubbles. So 3 people are over here. Right. So number of the sample space again, we said is, what is it? 80. Yeah. Okay, cool. Right. Now, we don't know what this is though, but it's okay. We can at least go and find those spaces in terms of X. Is that okay with you?
Yes, sir.
All right, let's look at the number of outcomes for only rugby. Let's look at that. So rugby should count up to 52, right? And this space over here should be 52 minus this, this, and this. You agree?
Yes, sir.
So let's go and subtract that. So that's 52 minus 14. That's 14. Minus X. Minus 12. Right. So what does that count up to?
26 minus X.
26 minus X. So this spot over here is going to be 26 minus X. Good. Now, this unknown spot at volleyball over here, we're going to go and look at that the same way. So the number of outcomes for only volleyball should be equal to 42, what?
Minus 14 minus 15 minus X.
Minus X. Good. What does that add up to?
13 minus X.
13 minus X. Good. So this spot over here is 13 minus X. And that's the Venn diagram. Great. 5 marks. Well done. You ready for the next one?
Yes, sir.
Now they say show that X is equal to 8. That means if you don't find that X is equal to 8, you don't know how they got 8. It doesn't mean you should stop with the question here. Or if you maybe found that X is something else, don't go with that answer. They're basically saying here that the X is equal to 8, but you should show us how we got 8. All right.
Yes, sir.
Right. So how do you think they got 8?
I'm not sure.
Oh, just deleted something. Well, think of it this way. Sorry, Pierre is asking me something. I'll be with you now, Mamelo. Just let me quickly answer his question. Pierre, have you got a question? Type fast. So for B, yeah, what do you want to say? I'm waiting. But we're going to carry on. If you got your question, you can drop it in there. I'm going to try and answer it afterwards. All right, Mamelo, let's carry on. So think about it this way, right? We know the total of the whole box. All the outcomes inside the box should add up to what?
80.
All right. So why don't we just state something truthful regarding that? I mean, then we're going to have this equation containing all these x's, and then maybe we can go and solve it. Don't you think?
Yes, sir.
All right. So how do you think this equation is going to look?
Maybe, I don't know, subtract everything, 80 minus everything. I'm not sure.
Well, 80 should be equal to what? 26 minus x plus 14 plus, carry on,
13 minus x,
13 minus x plus
15
15.
plus x
Yes.
plus 5 and plus 12.
But what about the 3? Remember, everything inside the box must
Okay.
add up to 80. So that means the 3 is included. You good with that?
Yes, sir.
All right, now we've got a nice equation over here. So let's try and solve this equation. Where does what go?
So
Are you one of those learners that simplify your left and your right before you start moving
Yeah.
things over? Okay, let's do that. So let's go and simplify all the numbers with the numbers on the right. It's going to be 26 plus 14 plus 13 plus 15 plus 5 plus 12 plus 3. Right? What do you get?
76.
Just again, just go and say 26 plus 14 plus 13 plus 15 plus 5 plus 12 plus
Oh,
3.
yeah.
What do you get?
88.
Yes, 88. All right, now all the x's, look here, minus x, and here's a minus x, and there's a plus x. What do you think they're going to do?
Minus x.
Plus x. They're
8.
going to cancel each other out, right?
Yes, 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 yes.
And then the only one that's left
Is minus x.
is minus x. All right, now where do we go now?
So you're gonna take the 80. Well, you're gonna take the 88 to the other side.
All right, so it's 80 minus 88, which is equal to minus x. Good, then.
Well, you're gonna simplify the other side, which is gonna be negative 8, and then you're gonna simplify it. So x is gonna be equal to 8 because you divided it by negative 1.
Brilliant. And then we've proven that x is equal to 8. Great. So next question, one more. Very easy. How many learners like only rugby? Only rugby, remember, is this part over here. So how many learners like only rugby?
18 learners.
Yes. How did you find that?
Well, I substituted the 8 in the place of the 8s.
Yes. So that's going to be 18 learners. Last one before we go on a break.
Okay.
They say calculate the probability that a learner chosen randomly likes at least 2 different types of sport. If somebody likes at least 2 different types of sport, what does that mean?
They like, I don't know, I'm not sure.
I mean, if I tell you like there's these 3 sports and Johnny likes at least 2 of them, What does that mean?
Well, 2 out of 3. I don't know. I'm really not
2
sure.
out of 3, or maybe 3
2/3.
out of 3,
What?
because it's at least 2.
Oh, okay.
At least means 2 or more. Does that make sense?
Yes, sir.
Right? So where are the parts where learners like 2 or more sports?
There by the center there. By the
The
blue.
center, that's where they like 3. Yes. Where do they like 2?
I'm not sure.
Come on. I mean, the green highlight that I put down there, that's for only rugby. And this is only volleyball. And this is only chess. So, I mean, and you just identified where it's all 3. So where are the parts where they only like 2?
By the 14, 12, and 15 there.
Yes. So that means we're going for all those purple parts together, right? And that's going to be, and because it's a probability, it has to be all of those together over the total in the sample space. All right, so that means the probability of at least 2 will be equal to what? 12 plus 14 plus 15 plus what?
Plus 8.
Plus 8. And that'll all be over what?
80.
80. Good. Now let's go and simplify that and give the answer to the second decimal. So first give me the fraction. 12 plus 14.
49 over 80.
That's 49 over 80. And what's that in decimal? Rounded off to the second.
0.21. 0.61. Sorry.
0.61. Yes. Perfect. Mamelo. So good. So good.
Thank you.
Right. Let me just zoom in here. All right. Who do we have next on the line? Culin. You can help me with this.
I can try, sir.
You can try. Okay, that's all I want from you. Just that you try. That would be great. Okay, so let's do this first question. I'm going to start off slow. Let's say, given the probability of A is equal to 0.6, the probability of B is 0.3, the probability of A or B is 0.8, where A and B are 2 different events. Now they ask, are the events A and B mutually exclusive? Justify your answer with the appropriate calculations and or a diagram. Now, diagram means you can either draw a Venn diagram, or with calculations, they mean you can either use one of those formulae that we spoke about earlier in the lesson. So which one do you feel more comfortable with?
I'm not really sure because we haven't done this yet. So,
well, the addition formula you guys have done in grade 10 already. So if you're comfortable, we can do that.
yes.
All right. Okay. So the addition rule, can you remember? It says that the probability. Let me just number this. The probability of A or B is equal to what? Can you remember?
No,
Check your
sir.
note. You can check your notes. There will be a formula. I think at the start of this lesson, there was a formula. The probability of A or B is equal to. It's called the addition rule. It's also called the identity, the probability identity. Can you find it?
No.
Okay, so the probability of A or B is equal to the probability of A plus the probability of B. Maybe I'm giving you more, minus something. Check if you can find a formula that kind of looks like this.
Okay. Is not the probability of A and B.
Yes, that's the one, probability of A and B. Now remember, they are trying to ask if the two events are mutually exclusive. What does that mean? If two events are mutually exclusive?
There are no outcomes in common.
They have no outcomes in common. So, I mean, on a Venn diagram, if you've got event A and event B, the two bubbles of event A and B, do they cross or are they separated in a mutually exclusive?
Separated.
They're separated. So that actually means that the probability of A and B in a mutually exclusive situation should be equal to what?
The sum of both. And
The sum of both, the probability of A plus the probability of B, right? Or even more so, because there's nothing here. Like numerically, the probability of A and B should be equal to what? Okay, not A, yeah, A and B. I think you gave the rule now for A or B. If they're mutually exclusive, the probability of A plus the probability of B will be equal to the probability of A or B. But if we have the probability of A and B in a mutually exclusive situation, because there's nothing here, what will be the probability of A and B?
the same? No.
There's nothing. I mean, what is the what numerical value is equal to nothing?
0.
0. So that means the probability of A and B should be 0. So if we can prove that this is 0, then we've proven that they are mutually exclusive. Does that make sense?
Yes, sir.
All right. Well, what do they give you? They give you the probability of A. So we can substitute that into this formula, right? So in the place of probability of A, we will put what?
0.6.
0.6. In the place of probability of B, what do we put in there?
0.3.
0.3. And the probability of A or B, what do we put in there?
0.8.
0.8. Now all we're going to do is we're just going to solve the probability of A and B. And if it's 0, what does that mean?
That they are mutually.
Now if it's not 0,
Then they are not.
they're inclusive then, eh?
Mm.
Right. So let's go and solve it. So consider this like you consider it's X, right? So let's go and solve that probability of A and B. What are we going to do?
So I would first add the 2, 0.6 and 0.3.
Which is equal to?
0.6, 0.3. It is 0.9.
0.9. Yes.
And then I'll move it over to the equals.
Right. So this is going to be 0.8 minus 0.9.
That would give us negative 0.1.
Negative 0.1.
Equals, yes. And then, so I used negative x to solve. And then, so I'll divide that by 1.
All right, negative 1. So that gives you the probability of A and B is actually equal to 0.1.
Yes.
So what does that tell me?
They are
The
inclusive.
probability of A and B is greater than 0.
And
Therefore,
they're inclusive.
A and B are inclusive, not mutually exclusive. Very good, Killen. Yes, great stuff. Right, you want to take on this next one?
Yeah, I can try it.
You can try. Okay, great. That's all I want from you, man. You can do that. I am eternally grateful. Right, let's just clean this up. Right, they say here, the table below shows data on the monthly income of employed people in 2 residential areas. Representative samples were used in the collection of the data. So we've got area 1 and area 2. In area 1, we have people that have an income less than 3,200. We've got 500 of them. Then we have people who get more than or equal to 3,200, but less than 25,600. We've got 1,182 of them. Then we have people who receive greater than or equal to 25,600, and that's 150 people. You get that?
Yes, sir.
Right. So you understand how area 2 works as well.
Yes.
Okay, good. Now they say, what is the probability that a person chosen randomly? A person chosen randomly means like all of the people in this survey are standing here in front of you. You're closing your eyes and you're walking into this group of people, and you're just going to put your hand on somebody's shoulder. All right. That's what they talk about if you're choosing a person at random. Now, they say, what is the probability that a person chosen randomly from the entire sample is from area 1? Now, how many people are in area 1 in total?
1,832.
And how many people are there in total in this survey?
2,646.
Great. So if the probability of area A is equal to the number of people in A over the number of people in the whole survey, what will the probability therefore be equal to?
So it would be 1,832 over the 2,000.
The 2,646. Right, let's go and simplify that, and then we'll give it in decimal. So type that into your calculator and give me the fraction. I can hear.
So the fraction is 916 over 1,332. No, 33.
23.
And
And what's the decimal of that?
It is 0.69.
0.69. Great. See, perfect. That's 2 marks. Great. Let's move on to the next one. Now, what is the probability that a person chosen randomly from the entire sample will be from area 2 and earn less than 3,200 per month? All right. Now, I'll show you a cool technique how you can go and find that. If you're dealing with an and situation, I tell my learners, take the 2 things that they're referring to. They're referring to area 2 and less than 3,200. Is area a column or is it a row?
The area.
The area, is it a column or is it a row?
A column.
It's a column. So take area 2 and just go and draw a line through that whole column. Right?
Yeah.
And now less than 3,200, is that a row or a column?
It's a row.
It's a row. Now take a line and draw that through the whole row. You see where the 2 lines intersect?
Yes, sir.
Where do they intersect?
At area 2, where x is less than 3,200.
Which is equal to what?
Excuse me, sir.
Which is equal to what?
460.
460. And that's going to be your numerator in your probability. So if you're looking for probability of area 2 and less than 3,200, that's going to be equal to what?
So would it be 460 over 96? 960.
No, because why not? Because they're saying that you're choosing a person at random.
At
In other
random.
words, all of the people here are in front of you. So how many people are in front of you before you close your eyes?
2,000.
Yeah. So that's
2,600.
2,646. Good. Let's go and simplify that. Give me the fraction.
2,046. As a fraction, it is 230
Yeah.
over 1,323.
And as a decimal to the second,
It is 0,17.
0.17. Brilliant, man. Right. At C, they say, what is the probability that a person chosen randomly from the entire sample space is a person from area 2 who earns more than or equal to 3,200? So same thing. They're saying area 2, so we draw a line straight through here. Or they're talking about or. Okay, that's very important. Okay, so think about it this way. So think about more than or equal to 3,200. Now, that is all of this. You agree?
Yes, sir.
Because that's all more than or equal to 3,200, even past the 25,600. And area 2, that's all of this, right?
Yes, sir.
Now, what I want you to do is add all of the blocks that you've made now. In other words, add all of this.
Okay.
What's that? 1182 plus 150 plus 340 plus 14 plus 460.
So I got 2,146.
Great. That's 2,000. So the probability here will be equal to 2,146 over what?
2,646.
2,646. Great. Now let's simplify that. How much is that?
46. As a fraction, there's 1,073
Over
1,323.
1,323. And as a decimal?
0,81.
0.81. Now, just before we go on, why did we color in or both those blocks? It's the same concept as when you have a Venn diagram. Say, for instance, you have a Venn diagram and you've got event A and event B. And I want to know what's the probability of A or B. Probability of A or B will be equal to all of this. You see how they intersect, but I want all of this, right? So it's the same thing here. You see, you've got event A, which is your area. You've got event B, which is your greater than or equal to 3,200. You see how they intersect here, but I want everything in there.
Yes,
Does that make sense?
Yes, sir.
All right, cool. Now let's look at this next one. You're doing well. Now here they say, prove that earning an income of less than 3,200 Rand per month is not independent of the area in which a person resides. Now, I want you to go through your notes quickly and look for the slide which says independent events. There will be a formula on that slide. Wyatt, I think you are raising a very good point here. I think I may have read that wrong. A person from area 2 who earns more than or equal to 3,200. Person from area 2 who earns more than or equal to 3,200. Culin.
Yes, sir.
Sorry, man. Wyatt is raising a very good point. I think I read that sentence wrong. And hey, I'm just a human being. I think because the word all caught my eye, I think I'm reading it wrong. Because now that I read the sentence again, I see they say, what is the probability that a person chosen randomly from the entire sample will be a person from area 2? So it's given that it's a person from area 2 who earns more than or equal to 3,200. So I think what they actually mean is area 2 and more than or equal to 3,200. Is that okay?
Yes, sir.
All right, so in that case, we're going to do that line method again. We're going to say area 2 and more than or equal to 3,200. That's this line and this line. Where do they intersect?
At 460, 340, and 14.
Just the 340 and the 14. You see, there's no line coming through here. Thank you, Wyatt. I think you are helping us out a lot here, because that's going to be 460. No, not 460. It's going to be 340 plus 14. Yes, which should be 354, but still over 2646, seeing as it's still all the people here in front of you. Okay, I'm going to go and simplify that. Thank you so much, Wyatt. 559 over 441. Each decimal is 0.13. Okay, let's carry on back with this question. Thank you, Wyatt. Right. So, Culin, have you found that page which says independent events?
Yes, sir. It's probability of A times probability of B.
So the probability of A and B is equal to the probability of A times the probability of B. Now, this is only true if the events are independent. Okay. So what we're going to do is they want us to go and prove that these two events are independent. Right. So what are the two events? They're talking about prove that earning an income of less than 3,200 per month is not independent of the area. If they just say area, it's not independent of the area. That means we can choose any area. Right.
Yes,
so we're going to go and find the left-hand side of this formula and work with it independently. And we're going to work with the right-hand side of this formula and work with it independently. The left-hand side is the probability of A and B, and the right-hand side is the probability of A times the probability of B. Good. Now let's look at the probability of A and B. Can you remember with A and B, we're going to use that line method.
Yes,
so we're going to say, all right, probability of A, let's call it less than 3,200. So that's this row, correct?
Yes.
Now choose any area, area 1 or area 2. Which one would you like?
Area 1.
Area 1. So we're going to make them cross. Where do they cross?
At 500.
At 500. So the probability of A and B is 500 over what?
The
2646. 2646. Good. Right. What's that simplified? 500 over 2646.
250 over 1,323.
1323. And what's that decimally?
0.19.
0.19. Good. Right. Let's look at this. Probability of A. What is the probability of A? Probability of A, we said, is the less than 3,200. What's the probability that somebody gets less than 3,200?
So would we say the total of A?
Yes. So the
Over
total
the
of
total.
of the total of the less than 3,200. What's that?
Yes. 500.
Total of less than
Oh, total.
3,200.
Yes.
What's that?
960.
960. So that's 960 over 2646 times the probability of B. We said B for us is area 1. So what's the total of area 1?
It is 1,832.
1,832 over 2646. Right, times those two with each other. Let's see what we get. 960 over 2646 times 1832 over 2646.
I got as a decimal, well, first a fraction. Oh, my calculator takes me straight to the decimal.
Yeah, what do you get?
0.25.
0.25. Now the question is, are these therefore independent of each other?
I would say yes.
Why yes?
So because if you times them, it would give you the probability of A and B.
Watch out. The probability of A and B here, we got 0.25. But
Oh, so they're
here we
not
got
equal.
that the probability is 0.19. So
Yeah, they
what
must
does
be
that
same.
mean? So what does that mean?
That they're dependent.
They're dependent because the probability of A and B is not equal to the probability of A times the probability of B, and therefore A and B are not
Dependent.
independent. They are dependent, therefore. Great. And that's exactly what they want. They want to say is not independent. And that's perfect. All right. Now let's now last question for you. Which is more likely? A person from area 1 earning less than 3,200 or a person from area 2 earning less than 3,200? So now we're basically saying that we've got all the area 1 people in front of us, right? And we have all the area 2 people in front of us. Now they want to know, what is more likely? A person from area 1 earning less than 3,200 or a person from area 2 earning less than 3,200? So we're going to work that out. So we're going to work out the probability of A earning less than 3,200. So picture this. You've got all the people in area 1 in front of you, right? All the people of area 1 in front of you. You're closing your eyes and you're walking into this group and you're putting your hand on someone's shoulder. I'm asking you, what is the probability that that person that you put your shoulder on, like your hand on, earns less than 3,200?
So would it be the 500 over the 2,600?
Watch out now. This is if all the people are in front of you.
Oh,
But
so
I
the
said
nine-
only the people from area 1 are in front. So that's 500 over 500 over what?
Is it the 960?
Oh,
Oh, no,
watch out.
the 1,832.
Yes. So that's 500 over 1832. 500 over 1832. Good. Now, what is that simplified?
As a fraction, it is 125 over 458.
And decimally to the second?
0.27.
All right. Now let's look at the probability of area 2 earning less than 3,200. Now again, you've got all the people from area 2 now in front of you. You close your eyes, walk into that group, you put your hand on someone's shoulder. What's the probability that you put your hand on someone's shoulder that has less than 3,200?
460.
Over?
814.
Yes, 460 over 814. So what is that simplified?
230 over 407.
230 over 407. And what's that decimally?
0.57.
0.57. Thank
Oh,
you.
6. Yes.
No,
0.6.
0.57, you're right. Now again, I asked the question, which is more likely? Which one was more likely?
The B, area 2.
So therefore, the probability of being in area 2 and earning less than 3,200 is more likely. Great, thanks, Kulan.
No problem.
Right, Bernati, you're asking why we're using the total of the area and not the total of the sample space? Because they ask here, a person from area 1. So it's given that you're working with the people from area 1. Same here, a person from area 2. So it's given that you're working with people from area 2. Does that make sense? When you're working out those two different probabilities. So if they say a person from area 1, which means you're just working with that.
So would that mean then if you were to say a person in area 1, then you would be including the entire sample?
I think you would say, if you would say you randomly chose a person from the sample space, is a person from area 1 who gets less than 3,200. I think that's when you work with the whole sample space.
So as long as it's specific, it would be the entire sample space.
If they say like a person is chosen randomly from the sample space, then yes, then it would be the total sample space. But here they're saying it's a person from area 1.
Okay, thank you.
That makes sense. All right. Sorry guys, now I've got dogs outside my house barking. Oof. Right, let me just clean up here. We can move on to the next one. Right, Humara, are you there? Did I lose Humara? Oh, hi, how are you doing? You doing well?
Yes, thank you.
Okay, brilliant. Okay, let's look at this next one. They say, at question 2.4, this is also DBE, exemplar 2013, question 12. They say a group of 33 learners was surveyed at a school. So this 33 learners, what does that tell you?
The total number of learners participating.
Right, so the number in the sample space should be equal to 33. You agree with that?
Yes.
All right, perfect. The following information from the survey is given. Now, they give here a Venn diagram, and I can see some letters missing. So I think from this info, they'll probably want you to go and determine the unknown letters, which is exactly what they want. So let's see if we can figure that out. We know that the sample space should be equal to 33 in the end. So they say 2 learners played tennis, hockey, and netball. Okay. Where do you see a 2 which accommodates that piece of information? Where do you see it?
It's in the center.
Here in the middle. Right. Now they say 5 learners play hockey and netball. So hockey and netball, that's this area here. All right. And that also corresponds with what they said here in the paragraph, correct?
Yes.
Okay. Now they say 7 learners play hockey and tennis. Now, hockey and tennis is this area over here. So what does that tell me about A?
It's 7 minus 2.
7 minus 2, which is equal to
5.
5. Perfect. So this is 5. I'm going to write it here. 5. Great. Now they say 6 learners play tennis and netball. Now tennis and netball, that's this area over here. So what does that tell me about B?
It's 6 minus 2, which is 4.
Which is 4. So this is 4. Great. So write this out. Now they say a total of 18 learners play hockey. So hockey is this whole area over here. So what does that tell me about C?
It's 18 minus 5 minus 2 minus 3.
Which is equal to what?
8.
That's 8. So this is going to be 8. C is going to be equal to 8. Brilliant. And then they say a total of 12 learners play tennis. So tennis, that is this area. So what does that tell me about D?
It's 12 minus 5 minus 2 and minus 4, which gives you
Which is
1.
equal- That gives me 1. That's 1. And then they say 4 learners play netball only. All right, and that corresponds with this. Okay, but that doesn't tell me anything about E. But can you maybe tell me what is E?
So you'll take 33 and minus everything in the circles.
Okay. And how much is that?
6.
6. Great. So this is 6. And E is therefore equal to 6. Brilliant. Cool. Now they ask me at the first one. How many of these learners do not play any of the sports on the survey? That is netball, tennis, or hockey. We just figured
6.
out.
By 33.
So that's 6 learners. All right, they don't ask for the probability. So don't put down 6 over 33 because that's the probability. They just want to know how many. Is that okay?
Okay.
Right, at number 3, write down the probability. Okay, here we go. That a learner selected at random from this sample plays netball only. How much will that be?
4 over 33.
Well done. 4 over 33. Can we go and simplify that? Can we simplify that fraction? I don't think so.
0.1. Oh,
0.12. Okay. Now, at number 4, determine the probability that a learner selected at random from the sample plays hockey or netball. Now, how much is that? Can you tell me?
is it 8 plus 5 plus 3 plus 2 plus 4 plus 4?
Yes, this is hockey or netball, all of that inside of that. So that's going to be, what's that going to be?
It's 26 over 33.
26 out of 33. Can we simplify that? 26 out of 33. Nope. But what is that in decimal?
0.79.
0.79. Kumara, that was perfect. Thank you so much. Do you want to try this next one?
Sure.
You ready? Or
Okay.
can I give Diana a call next up?
Yes. Thank you.
Okay, cool. Thank you, Mara.
Yeah.
Right, Diana,
Hi, sir.
how you doing?
And you?
I'm good, thanks. Right, let's look at this. So they say in all South African schools, every learner must choose to do either mathematics or mathematical literacy. a certain South African school, it is known that 60% of the learners are girls. The probability that a random chosen girl at the school does mathematical literacy is 55%. The probability that a randomly chosen boy at the school does mathematical literacy is 65%. Determine the probability that a learner selected at random from the school does mathematics. What method would you want to use to go and determine this probability?
I would do a tree diagram.
That's perfect. Let's go. So in order for us to go and find out this probability, we need to be there. So here we are. So let's say we first have to go, how are you going to do this? Are you just going to go for like mathematical literacy and maths first, or do you first want to go and sort out the gender?
I think gender.
Gender is good. All right. So let's start with picking the gender. So if you choose a learner at random, what are the possible outcomes that you can have with regards to gender?
Either male or female.
Either male or female. Good. Now, what is the probability that it would be male if they say 60% of the school are girls?
40% for male.
So that would be 0.4 for male, and how much for female?
0.6.
0.6. Very good. Now let's say you chose a male. Now we need to go and pinpoint whether they have mathematical literacy. So I'm going to write down here ML or just PM for pure maths.
Okay.
Right. Now they say the probability that a randomly chosen boy at the school does mathematical literacy is 65%. So on the ML branch, what will be the value that we're going to slot in there?
That would be 35%, 0.35.
Hold up. They said the probability that a chosen boy at the school does mathematical literacy is 65%. I think you're already going for pure maths now. So for mathematical literacy, it should be what?
Would be 0.65 and
Yes, sorry, 0.65. And then pure maths?
pure maths is 0.35.
Yes, perfect. Right, that's sorted. Now for females, again, we're going to go and sort out whether they have mathematical literacy or they have pure mathematics. Now they say here, the probability that a randomly chosen girl at the school does mathematical literacy is 55%. So on the ML branch, what would we have there?
0.55.
0.55. And on the pure maths branch?
0.45.
0.45. Great. So our whole tree diagram is actually sorted out. Now we can answer the question where they say determine the probability that a learner selected at random from the school does mathematics. Good. So you can either have two different situations, right? You can either have a male who does pure mathematics, or you can have what?
A female who does pure mathematics.
Yes, so that's our or situation. We are going to work out the probability of male and pure mathematics or female and pure mathematics. And again, what does or mean?
Addition.
Addition. So let's go. We've got male and pure mathematics. That's going to be a product of what?
A product of 0.4 multiplied by 0.35.
0.4 times 0.35 plus
0.6 and 0.45.
0.6 times 0.45. Good. And what does that give me?
Okay. Okay. So the boys is 7/50 and the girls is 27/100.
0.4 times 0.35, 7 out of 50. Plus 0.6 times 0.45, which is 27/100. And what's that in total?
41/100, 0.41.
100, which is 0.41. Diana, that was perfect. Thank you so much. That was great.
Yep.
Right. Let's move on to this next one. Victoria, you can help me with this one. Victoria, are you there? Okay, I'll move on to Mamelo. You can help me with this one. Ah, Victoria, you're back. You can help me with this one. I'm going to switch on your microphone. All right, okay. So Mamelo, you can help me with this one. You can switch on your microphone.
Okay, sir.
Okay, perfect. So they say on a flight, passengers could choose between a vegetarian snack and a chicken snack. The snacks selected by the passengers were recorded. The results are shown in the table below. All right, so they've got vegetarian, they've got chicken, they've got male, they've got female. They show all the totals of the vegetarian, they show all the totals of the chicken, show the totals of the male, show the totals of the female. And this 150, what does that refer to?
Well, the total for everything, both female.
All the people on that whole thing.
Yeah.
Right. So it says here, was the choice of snack on the flight independent of gender? Motivate your answer. So if there's a choice of snack, that means we can choose any snack. And if they say independent of gender, that means we can choose any gender and we can work out whether they are independent of each other. Can you remember what the independence rule is?
No, sir.
We worked with it earlier. I think I wiped it out. Yeah, unfortunately, to make some space. So go to your notes and you'll see there's a slide which says independent events. There's a formula on it and recite that formula. Do you have your notes with you?
Yes, so let me just get to it.
All right.
Yes, and okay, I'm still looking.
That's fine. I'm setting it up for you, Salon.
Okay, independent events.
Yes. What's the left-hand side of that formula that they give there?
It says P, A, and B.
So the probability of A and B. And what's the right-hand side?
P and B. No, sorry.
PA
Times PB.
times PB. Right. Now, if the left-hand side is equal to the right-hand side, then the two events are independent. So we're going to prove that the two sides are either equal or not equal, and we're going to make a logical deduction from there. Is that fine?
Yes, sir.
All right, so let's start with this left-hand side. The probability of A and B. Now remember, A and B is in a general sense. So let's say choice of snack is A and gender is B. So you need to make a choice with regards to snack, right? Which snack do you want to talk about? Vegetarian or chicken?
Vegetarian.
Okay, so we'll make this vegetarian. And gender, you have to choose a gender which you want to talk about.
Male.
Male. All right, so this is going to be B. So they say, all right, we're first going to go and find the probability of A and B. And you remember earlier, I think I worked was with Cullen. I told him this method where you can work with lines to find the and.
Yes, sir.
All right, so for A, it's a row. So we're going to draw a line down the whole row. And B is male. So we're going to draw a line down the whole column. Now we're going to ask ourselves, where do they intersect?
At 12.
At 12, right. So the probability of A and B should be 12 over the total of all the people. What's the total of all the people?
150.
150. Can we go and simplify that? What do you get?
2 over 25.
And decimally to the second?
0.08.
All right, perfect. Okay, now the right-hand side, we're going to take each of these individually. The probability of A. In other words, the probability that somebody is a vegetarian. What is the probability that someone is a vegetarian amongst all of these people?
32.
32 out of
150.
150. So that's 32 over 150. And what's the probability that someone is male amongst all these people?
118. No,
Male, not eating
67,
chicken.
sorry.
67. That's
67.
fine. No worries. 67 over
150.
150. All right, let's go and times those two with each other and see what we get. 32 over 150 times 67 over 150, which is equal to what?
536 over 5,625.
5,625. And that's simplified into decimal is what?
0.10.
0.1. Okay, now look at these two, the left-hand side and the right-hand side. Are they equal or are they not equal?
Not equal.
So that means the probability of A and B is not equal to the probability of A times the probability of B. And what does that tell me?
It's dependent. It's not-
Yes, that snack is dependent on gender. Right. Or snack is not independent of gender. Does that make sense?
Yes, sir.
All right. Cool. That's that. Great, Mamelu. Well done. Thank you very much.
You're welcome.
Right. Keelan, you're going to end the day off for us. You ready for this?
Yes,
All right, let's do this. So they say, for any two events, A and B are given. It is given that the probability of A and B is 0.12. The probability of A or B is equal to 0.83. Then they say the probability of B is equal to 4 times the probability of A. Now, first question they ask, are the events mutually exclusive? Justify your answer. All right. So, first of all, we don't know what the probability of B is or the probability of A. Does that make sense?
yes,
Right? So, is there a way that we can maybe figure out what is the probability of B and the probability of A if they already give you the probability of A and B and the probability of A or B? I mean, we worked with a formula earlier that contains A, B, A and B, and A or B. Can you remember that formula?
Is it the independence?
Not independence, but there's another one which contains all 4 of them.
So is it mutually exclusive?
Third time lucky. It's another one. It kind of looks like the mutually exclusive rule, but it has an extra tail attached to it.
I'm not too sure.
Well, let's think about it maybe in an easier way. If two events are mutually exclusive, right? Maybe this would be a little bit easier. Maybe we can leave the probability of B and the probability of A alone for now, because I see they ask it here and they ask something about not A over there. So maybe there's an easier way to think about it. If two events are mutually exclusive on a Venn diagram, does that mean the two bubbles intersect or are they separated?
They separate and therefore zero.
Separated. Right, so there's nothing in between the two. So what does that mean for the probability of A and B? It should be equal to what?
0.
0, but look here. What is it
Okay,
equal to?
so it's equal to 0,12, which means that it
0.
is not.
So which already indicates what?
That it's not. That it's
It's
inclusive.
not. Yes, so we can say no, but what would be our reason?
Because it does not equal to 0.
Is not
Probability
equal to 0.
equal to 0.
Perfect. Great. 2 marks. 1, 2. Now, the next, they say calculate the probability of B. Okay, back to that drawing board. There's a formula which states that the probability of A or B is equal to the probability of A plus the probability of B minus what?
The probability of A and B.
And B. Okay, let's go set in what we have. We have the probability of A or B. What's that equal to?
0,83.
0,83. We have the probability of A and B. What's that equal to?
It is 0,12.
0.12. Now, we don't know what probability of A is. We don't know what the probability of B is, but it's okay because they say the probability of B is equal to 4 times the probability of A. So we can rewrite the probability of B as what?
4 times P. P A.
All right. So again, see the probability of A as X. Right? So we want to go and solve X. Good.
Yes.
So how are we going to do this?
So with the 4 probability of A, would that be like 4 times X?
4 times X, yes. 4 times X plus 1 times X is equal to?
4 times X.
Watch out. What's X plus 4X?
Oh, that's 5.
That's 5X. So that makes this 5 probability of A, correct?
Yes.
Right? And we still have the 0.12 and the 0.83 over here. Okay, so what do we do next?
I'll take the 0.12 over and add it to the 0.8.
Okay, so 0.83 plus 0.12.
And then I'll
Good.
divide that by 5.
Okay, 0.12, divide that by 5. What do you get?
0,19.
0.19. Now, because we know what the probability of A is, and we know that the probability of B is therefore 4 times that probability of A, which is 0.19. What does that make the probability of B?
It would be 0.76.
0.76. Great. That's 4 marks. And now they ask you to calculate the probability of not A. Okay, now there is a rule for this. The probability of not A is equal to, now go and look for that. Go and look on your slides which says complementary events. You'll see there. The probability of not A is equal to what?
It is equal to 1 minus probability of A,
1
which
minus
is
the
equal to
probability of A,
probability of
which is 0.19.
0.19.
0.19. And what's 1 minus 0.19?
It is 0.81.
0.81. Perfect. Kulan, great stuff. Did you learn a lot today?
I did. Thank you, sir.
Perfect, man. Great. Thanks, man. Right. Grade 11s. I still have like 1 minute left. Are there any last questions about these questions that we did that you guys would like to ask? Please like put up your hand or send me a quick chat if you have any last questions. Just let me know if you have any questions for this last minute. Maybe go over something quickly. I'm going to make that 1 minute run out. So please, if you have any questions, anything that was unclear to you, something that I said that doesn't make sense, something that I said that you were just like, why, where did he get that from? Just put your hand up quickly, or switch on your microphone, or type in a chat. If you have no question, then just type no. No more questions, sir. Thank you. Just type into the chat. Just let me see. Thanks, Wyatt. Right. No more questions. Rutendu, so to clarify, is not A and not B the same as not A or B? Not A or B. Okay, so not the probability of not A and B, and the probability of not A of not A or B. Okay, let me quickly check. Let's draw a Venn diagram. Rutendu's got a question here, a very nice question actually. She asks, is the probability of not A and B the same as the probability of not A or B? Let's see. So we've got A, we've got B. So not A and B. So A and B is this over here. And not A and B is this over here. Everything outside of that. All right. So that's the one. So let's look at another Venn diagram. Let's see if we get the same thing. Whatever. Here's A, there's B. So not A or B. No. So this is B, and all of this is still not A. So Rutendu, you can see these two are not the same. See, all the highlight is what we want.